Hi, let's set the context for this next module that is called plane stress. Right, this is one of my favorite modules because it actually includes and embraces all of the stress models that you've learned to date. You'll see a whole lot of things here on this page about some technical details, but all we're going to do in this video is really just set the context, a very important context, because if you don't, you'll understand the big picture here. You'll get completely lost in the mathematical details. All right, so let's take a look at a typical highway overpass sign. This particular one is in the state of Indiana, my home state, but you'll see similar kinds of overhead signs on the highways of this state of Utah. And so on that sign, you might have a variety of loads that it has to resist. You've got the obvious self-weight of the system, and that the part of that large weight will be out there where the sign itself is located. But then when the wind blows, you have this large catch area that is going to also create a number of different effects, right? And all of which are fairly significant. So let's take a cut through that base of this support pylon and see what might be going on here. And it's pretty complicated. You have that sort of gravity load, that's the axial load in the column, that's P. The wind is trying to twist that pylon around, that's your torque T. You've got also the self-weight trying to create bending about the z-axis. The wind is creating a shear down the z-axis, and wow, you've got this additional bending moment that comes from the wind as it tries to bend this thing about the x-axis. All the stuff that you see here is what we would just call statics, three-dimensional statics, but it's just the statics. What we've been learning in this course is how to take each one of these internal resultants and turn them into some sort of a normal stress and some sort of a shear stress on a little tiny portion of the cross section. Wow, all of that work, statics work, and then some basic stress models in this course just to get down to this basic level that really becomes a two-dimensional state of stress, right? There's, visualize a tiny little cube, and on four surfaces, and really that means two dimensions, top, bottom, and the two sides, left and right, you'll have some normal and shear stresses. On the other two sides of our six-sided cube, you'll have no stresses. That's a state, mathematically, that we would call plane stress. Some physical examples, in addition to the very complex one that you just saw with the highway over sign, some simple ones are cylindrical pressure vessels, spherical pressure vessels. Both of those that you see here are ones that you might see in industrial settings. The hot air balloon is also an example of a plane stress condition. We would tend to call, in that case, the stresses membrane stresses for them being in the membrane of this hot air balloon envelope. And that's why, if you go back to these two pressure vessels that are in the industrial context, we'll sometimes call those stresses also the membrane stresses. That's the plane that we're focused on, is the plane of the membrane. You will also, though, see this being able to be applied, as we suggested or hinted at in the highway over sign, but in this structure that you see on screen, you have a variety of steel pieces that are making up various aspects of the structural system for a steel frame building. And up sort of over to the upper right is a simple statics model that represents one of those cantilevered beams. And we can use these plane stress models for that situation too. Same as in this, visualization of a new picnic gazebo at a beach location. We can use these kinds of models so that they have a wide range of application. On the other hand, there are conditions where those models don't work as well. And dams, these long, thick structures, systems that you don't have these long, skinny little pieces, or these pieces that are trying to be expanded, like the pressure vessel problems. Instead, these big, thick, solid types of situations are more examples of plane strain as opposed to plane stress. Right? And so you have the dam above, and then here's one a little bit closer to the state of Utah at the Glen Canyon Dam. This is one of my favorite locations in all of the continental US, because we have this beautiful bridge that's a nice arch truss bridge, and then we also have this curved gravity dam here that's That's also an arch dam, as well as having some gravity aspects to it as well. Wonderful, beautiful examples here of civil engineering structures. All right, so let's get into a little bit more precise definition of what plane stress and plane strain really means. You want to be thinking in both cases about two dimensions. Plane, that's what the plane is all about. All the action is happening in the plane, and in a sense, nothing is happening outside of the plane. So plane stress refers to what happens within the plane, sort of like a sheet of paper, but out of the plane, the stress is zero. The normal stress and the shearing stresses are zero. In plane strain, on the other hand, in the plane, the strains are not zero, but in the third dimension, both shear strain and normal strains would be zero. And that's that yin and yang thing that's going on here. You could think about it like this, back in the plane stress condition. We can stretch it within the plane, and Poisson's effect means that it will shorten in the other direction, or we'll squeeze it in the plane, and then it'll bulge in the third direction. So there'll be a strain in that third direction, although there's no stress. In the other example, we're going to prevent that strain in the third direction, which means we're going to have a stress that's not zero. And that's, again, that yin-yang that's going back and forth. In this first course in Mechanics of Materials, we will focus on plane stress conditions. All right, so mathematically, let's give you a quick kind of overview of where we're headed. The typical kind of situation is that we apply these models that we've learned of sigma equals P over A, or maybe sigma equals MY over I, or the tau equal VQ over IB, maybe even tau equal T rho over J. Right, going back to that highway sign example, we got all of that kind of going on. But we'll reduce it down to this two-dimensional problem, plane stress, and we'll be asking the question, okay, well, those basic models gave us those normal stresses and shear stresses, but what about other planes? Are there normal stresses that are larger than what we see in just the X and Y planes, or shear stresses that are larger? If we're going to design the system, we got to figure out where those maximums are located. That's one typical kind of scenario. Down lower on the page, what you see is the manufacturing system for a typical civil engineering structure that is a pipe. Right? You may not think of that as a structure, but it is very much so a mechanical system that is meant for fluids to flow through it. The way that many of these pipes, if they're metal, are manufactured is through a helical wrapping approach. So the steel manufacturer will create the plate steel that comes in a big roll. It gets then rolled out into a flat sheet, and then that flat sheet is wrapped in a helical fashion, just like a paper towel tube would be done. Somehow, though, you have to bond that all together. The paper towel example, you'd use glue. Here with, of course, steel, we'd use a welding process. And one of the critical questions that's going to be is, well, what are the stresses that are normal or normal or parallel to the weld itself, the weld axis, right? And so that's why we have to be able to go from maybe the X and Y coordinate into a different set of coordinates, right? Now, a truly big picture from a math standpoint is, again, looking at this two-dimensional thing in the plane, and then we'll rotate it and try to figure out, well, what are those stresses that are on that inclined plane? And these equations that you see down below are those models that we're going to learn where they come from, and then we'll learn how to apply them, and then we'll start to learn not shortcuts, but simpler ways to visualize what these things are, because these are intense, right? And although we have software that will give us, we'll just plug in the values and out pop answers, but visualizing that, understanding what that information is, right? And did we even do data entry correct? We can get there very quickly with a couple of visual techniques that will help us. That visual technique will be called Morse circle. So we'll learn how to do both the plug and chug variety, as well as being able to do a quick quality control and visualization, right? So next what we'll do is go into the basis of the derivation of where those things came from, and then we'll get into some applications.